if we pick up from where we left off, I think we ended yesterday with Schrodinger and his unfortunate story about dead cats, right? So I'm not sure why that was the appropriate way to do this. But now we're going to kind of see what this means to high school chemistry students. All right. So what we got to learn is identifying where these electrons are. I think we said this yesterday, right? Chemistry is a harder science to learn because it's more theoretical. It's hard to see. And one of the things that's really hard to see are electrons. And they are arguably the most important thing in chemistry. I think we came to that conclusion yesterday. Yes? Okay, at least some of you came to that conclusion with me yesterday, that electrons are the most, if not the most important, the most interesting thing in chemistry, because that's what a chemical reaction is, the moving of electrons. Good. So now we're going to learn how to identify where those electrons' ground state is. That's kind of what these quantum numbers are going to tell us. Okay, so these quantum numbers, they describe the properties of orbitals and electrons around the nucleus. Great. Not really sure what that means. Kind of like an address. Okay, so if you think about it like an address, we can give the electrons an address. There are 4 quantum numbers. 3 of them you're going to actually give values to. One of them, it's kind of beyond our level. Two of them, you already know how to do. Huh? We call that pre-teaching. Everybody ready to learn the first of the 4 quantum numbers? By the way, the quantum numbers have nothing to do with being really, really small. Ant-Man is not reality. It's not real. Yeah, remember, a quantum is a packet of energy. Yeah. Right? And that packet of energy can be a photon, or it can be an electron, or it can be any other packet of energy. Right? Quantum are just these discrete small packets of energy. That's what we call them. Okay, your first quantum number is called the principal quantum number. It has a symbol of a lowercase italicized n. So if I ask you this question on the quiz and you don't write it in italics, it's wrong. I'm just kidding. I don't know how to write italics. This gives what's known as the main energy level. When I say level, and we're talking about electrons, what do you think I mean? What is level 1? The first ring. What is also level 1? Everybody look at your warm-up. What's level 1? Helium. Hydrogen and helium, right? So you already know these energy levels. They are number 1 through 7. And what could you say about the lower numbers? Can you make any hypotheses about the lower numbers? Okay. They're the furthest. Right? The lowest numbers are the furthest from the nucleus? No. Here's what I'd like you to do. I'd like everybody to make a hypothesis about the numbers. What does the lowest number correlate with? And I'm being intentionally vague. Write down, don't verbalize. Please write down in your notebook, what does the lowest number represent? What does it correlate with? Write it down. 10 seconds. Okay, pair up. You guys look that way. You guys look that way. You guys look that way.
I could do the leap out of energy. I put like the natural.
Okay, who thinks they've got a good answer? The good answer cannot be Spencer, what'd you guys come up with back there?
Most amount of energy. Most amount of energy.
All right. What I'm hearing is lowest number, most amount of energy. How many other groups came up with a similar answer to that? How many people came up with the antithesis of that? The antithesis? The opposite. Here's a question for you. Everybody look at your periodic table. Which elements do you think have the most energy? Which ones have the most energy? Which ones have the least energy? Do we have anything in our lives which tells us this? The periodic table, okay. How many people know what a bomb is made of?
Hydrogen.
Not a hydrogen bomb. Not an atomic bomb, guys. A regular old bomb.
Uranium. Gunpowder.
Like what powers a bullet?
Gunpowder.
What's gunpowder made of? Pretty sure it's just carbon and nitrogen, guys. Explosives are made of nitrates, nitrogen. Right? Look where nitrogen is. Right? That sounds pretty powerful, doesn't it? What's more powerful, a nitrogen bomb or an atomic bomb? What's an atomic bomb made of? Uranium. Which one has more energy? Uranium. That's not an exact correlation, but that's a good way to understand which ones are at the top. The top of your periodic table. What level are they in? Which ones are at the bottom? Yeah. Don't they have more energy?
Yes.
So this tells us that the lower the numbers, the lower in energy. And as you identified, the lower the number, the closer they are to the nucleus. Okay. Everybody good with that? That's your principal quantum number. That's a number 1 through 7. Its symbol is N. Angular momentum quantum number is a bit more complicated. Look at all these crazy drawings I got, guys. Yes, they're crazy, right? This actually is way easier than you think it is. Your angular momentum quantum number has the symbol of a lowercase italicized L. Not a cursive L. That's length. Lowercase italicized L. This gives the shape of the sublevel, which sounds confusing, but you don't really need to know that. What you need to know is this is S, P, D, or F. And we already learned this, didn't we? You know where S is, you know where P is, you know where D is, and you know where F is. So if I were to say, name me an element in 3S, could you do it? Or sodium or magnesium. Can everybody find sodium and magnesium? Can everybody see them in 3S? Yeah. Name me an element at the end of 4P. Krypton. For all you Superman fans out there. Okay, here's something that's interesting. In each level of the S orbital, how many elements are there? Or the S block, sorry. There's 2, right? Okay. How many elements are there in the P block in each level? So how many are in the D level or the D block? And how many do you think are in the F block? Without even counting.
14.
14. There are half the amount of orbitals as there are elements. Why indeed? Why indeed? Maybe because each orbital can hold 2 electrons. Two of these you need to know the shape of. 2 of those, we're not going to go there. The first one's pretty easy. An s orbital is a sphere. It's spherical. So everybody stop copying and take a look real quick. 1s, 2s, 3s, 4s. These are like Niels Bohr imagined. Niels Bohr imagined that it was just a sphere, concentric circles around the outside of the nucleus, where all of these electrons existed. Right? That's how Niels Bohr gave us the electron diagram. Right? Niels. I'm pretty sure it's just Nils. Niels. He was a player on my baseball team. Shout out to Niels. YouTube shout. They watch all my videos. All of my 9U baseball players. The p orbital is different. The shape of the p orbital is fundamentally different from an s orbital. This is something Niels Bohr did not understand. Most people describe them as a dumbbell. Anybody see the p orbitals up here? They're in this greenish color. How there are 3 dumbbells, and they go on the x, the y, the z axis. This is my cheerleading practice. The x, the y, and the z axis, right? X, Y, Z. That's what those are. These are the p orbitals. You have to know that they are those shapes, the shape of the dumbbell. Some people think they're kind of opposing teardrops, I guess. In the d orbital, they get a little weird. Remember I told you yesterday the d block starts to act weird? The p block starts to act a little weird. The d block starts to act a lot weird. And the f block, you guys want to see those? Please make sure you memorize all of these. Yeah, exactly. You don't have to. No, that's not even an AP chemistry. No. Beyond AP chemistry. Okay. All right. So does everybody understand angular momentum quantum numbers? How many different values can I put for my angular momentum quantum number? How many different values are there? 4. What are they? S, P, D, and F. If I told you to find an electron that's in 3s, you could find it, right? Look at your periodic table. Go to level 3, look in the S block. It's one of those 2. Have I told you 6p? You could find it, right? It's one of those 6. Good? So you see how this is like an address? Okay, the next one's called a magnetic quantum number. This is the one where we're not actually going to apply a value to it. Because it's too complicated, really. Its symbol is a lowercase m. This is actually italicized. Please write it in italics in your notebook. We say that this gives the orientation around the nucleus. Right, so if I'm in s orbital, I only have one shape. There's only one orientation. If I'm a p orbital, how many different orientations can I be? 3. I can either be, yeah, go fight, win. Everybody ready to? I know, right? Because I'm a survivor. Okay. If I'm in the p orbital, there are 3 different orbitals I can be in. the x, the y, or the z. The d orbitals get weird. I don't know if you can see their names from where you are, but I got the first one's called x squared minus y squared, xy, yz, xz, and z squared. You don't have to know any of those. We're not going to actually assign this number to anything. Good? I'll show you how we use this probably tomorrow. That indicates which orbital it is in the subblock. And then we got something very interesting next. It's called the spin number. The fourth and final quantum number is the spin number. What did we learn about electrons yesterday? Did we say this in class yesterday? Aiden, there's something I need you to remember and tell us all year long. You ready for this? Electrons don't like each other.
Electrons don't like each other.
All year long. This is going to be a fundamental concept that we come back to all year long. Remember when we drew the board diagram yesterday? Yeah. And I drew them separately? That's because electrons don't like each other. Good? Electrons don't like each other. And that's what the spin number is all about. If I have two electrons next to each other, they can't be spinning in the same direction. They have to spin in opposite directions. Otherwise, something happens called a magnetic field, which I'm not really sure what that's all about. And I don't know how a magnetic field is different than a gravitational field. They apparently are fundamentally different, but I don't understand why. Wow. Because of this, electrons have to spin in opposite directions. Why, Kate?
They don't like each other.
Because they don't like each other. And this spin number is an arbitrarily assigned number which shows them spinning in opposite directions. So for some reason, we could have chosen any digit we wanted to show opposite directions. And you know what we chose? +1/2 and -1/2. So if my electron is spinning this way, it's a +1/2. If it's spinning this way, it's a -1/2. Because I am clearly not the king of science. If I were the king of science, it wouldn't be a plus and minus 1/2. That's ridiculous. I would just use 1. Plus and minus 1.
Do you think there's a reason why somehow?
Yes, and I'm sure some really smart physicist / chemist had a really good idea for why they did it that way. I don't know what it was. And maybe I do know what it was, but I'm not smart enough to understand it. Eventually, I'm going to get back to doing that list. Maybe I'll do that tonight because my baseball practice is canceled. And I'm not watching the Yankees tonight, as we talked about earlier. That's not for you. Okay, so are we ready to learn the practical application of everything we've talked about for the last 2 days? No, it's just +1/2 or -1/2. Yeah, it's just NLM. Yeah, why don't they even go in order? It's ridiculous. I get N because that's the number, right? L is not a number. It's SPD or F. Okay, so electron configurations. In electron configurations, when we do this, there's 3 rules. And you know what? Yeah, let's do the rules really quick. Let me put them up here. Okay, you can write these down all you want to. Aufbau principle. Aufbau is German for to build up. How many people speak German? Okay, good. Aufbau means to build up. So when we build these up, we always build from the lowest energy level to the highest energy level. Because if you try to put something in the highest energy level before it's in the lowest energy level, it falls back down. And as it's moving down, it screams out and a photon is emitted. Right? So we're going to build from the bottom and move our way up. Like building a pyramid. Not going to build the top of the pyramid before you build the bottom of the pyramid. You have to build the lowest energy level first. That's Aufbau. Hund's rule says I have to place 1 electron in all the orbitals of equal energy before putting 2 electrons in any one orbital. That'll be more clear later when we do tomorrow when we walk through orbital diagrams. I'm going through this super fast because I want to get you to electron configurations today. Finally, the Pauli exclusion principle. This, as Caden definitely knows, is because
The electrons don't like.
electrons don't like each other. So if I have two electrons sharing the same orbital, they must spin in opposite directions. Do they want to share the same orbital? Absolutely not. That's Hund's rule. They don't want to share the same orbital. If they have to, they will. But when they do, they're going to spin opposite directions. So Aufbau, Hund's rule, Pauli exclusion principle. I'm going to need about 5 minutes. So we're going to, if you're not done copying, we can pick this up tomorrow. Right now, I want to do an example. We're going to do 2 easy examples to start. When we're doing what's called an electron configuration, all you're doing is showing me where all the electrons are. So let's start with, Ryan, what's your favorite element?
Oxygen.
I love it. That's exactly what I was thinking you were going to pick. I should have written it down. Oxygen. There we go. Good. How many protons does oxygen have?
8.
8. If it has 8 protons, how many electrons does it have?
8.
8. Good. 8 electrons. So what I'm going to do is I'm going to tell you where all these electrons are. And I'm going to start at the lowest level, right? Hund's rule. Start at the lowest level. Or is that Aufbau? Aufbau rule, sorry. Aufbau, build up. Start at the lowest level. So the lowest level is what level? 1. And which block is first in level 1? SP, D, or F? So it's 1s. How many electrons can I fit in 1s? 2. So I put a superscript there as if it's 1s squared. I don't. I call that 1s2. And then I put in 2 electrons. So I have 6 electrons left. Agreed? What is next? Okay, what's in 1p? Look at your periodic table. What's in 1p? Say it again. There's nothing in 1p. So we skip it. Where do we go? 2s. Good. How many electrons can go in 2s? 2. I got 4 electrons left. What comes after 2s? 2p. Okay. How many electrons can go in 2p? 6. Yes. How many do I have left? 4. That is the electron configuration for oxygen. Done. That's it. You've told me where all of the electrons in oxygen are in their ground state. 1s2, 2s2, 2p4. Not so bad. Okay, let's try magnesium. Okay, magnesium. What's the atomic number of magnesium? 12. So how many protons do I have? So how many electrons do I have? 12. Okay, what's my lowest energy level? 1s. How many go there? Okay, what's next? 2 go there, sorry. Okay, what's next? 2p. How many can go in p? 6. Do I have 6 left? Okay. What's next? How many can go there? How many do I have left? Oh, man, that's pretty good, doesn't it? That is magnesium. Remember when I said things start to get weird in the D block? Well, things do start to get weird in the D block. I have more than a minute left. Let's see if we can do manganese. Mm. Okay. I don't think I can do this. I'm going to run out of time. My goodness. We got plenty of time. Good. Let's do manganese. I thought we were done it at the top of the hour, not 9 minutes after the hour. All right, good. Let's do manganese, guys. We'll get to that guy in a second. That's going to be really important. They're going to need it. All right. How many protons does manganese have? 25. So how many electrons does it have? 25. Okay. I think you're starting to see the pattern now. How do we start this? 1s. Then what? Then what? Then what? Then what? Then what? 4s. Then what? 1d? 4d.
4P.
4. I got. You guys want to know a secret? 3D comes next. Everybody look at your periodic table. Everybody was wrong. Okay. Take a look. Look at the level 4D. Look above it where 3D should be. I want you to imagine there are invisible blocks above that. And we're going to fill those first. Bit ridiculous, isn't it? Do you know why we have to do that? No, because things get weird in the D block, guys. Things get weird. The good news is you don't have to memorize this. I'm going to put up that chart that you see in the back of the room. Every time you have an integrated event, this tells you how to fill it. And I'll show you how to do that later. But right now, you know that 4s goes before. Good? So now I need to get to 25 electrons. You guys want to do this the long way or the short way?
Sure.
Okay. I know 2, 4, 10. At 2p, I'm at 10, yes? You know how I know that? What element stands at 2p6? And what's its atomic number? So how many electrons does it have? Good. Okay, and then I could do the next thing. -8, right? So now I think I'm down to 7. Right? Everybody see what I did? Okay, so now I've got to deal with 4s. How many can go in 4s? 2. So I take 2 off of there. I've got 5 electrons left. How many electrons can go in the 3D level? And how many do I have left? 5. So I just put a 5. And I'm done. That is the electron configuration of manganese. A little bit weird because 3D comes after 4s as opposed to, unfortunately, 4D after 4s. Okay, since I know now that we have 7 minutes left, I would like you guys, the first thing I'm going to show you is this. And we start at these arrows. Start here. 1s, 2s, 2p, 3s, 3p, 4s. Yes? Then 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s. Because that's the way it goes. Yes.
I feel like the other things on the like letters, is that like how many there are in that row?
Yes. right? That's the number of electrons that can fit in that level in that lock, right? So P, when it's full, is always going to be 6. So I'd love it if you guys could all give me the electron configuration of radon, please. Radon.
86.
Are you sure? I'm sorry. Radium. I'd like you to give me radium, not radon.
Is what they're 40 What about Lorium?
Is it DOHR? That's what
Wait, we're 3 people.
88. For reals, with a Z. Come on. He was never that handsome.
Wait, but there's 80. Look at there's 80.
Wait, it's 2 hours.
What? That was yesterday.
1S, 2S.
88, guys. It's number 88.
So there's 80.
Yes.
It does.
Yeah. 88. And to make you all extra mad when you're done doing all 88, I'm going to show you which one.
What?
So how many blocks are in the
No. Not even close. Guys, you know it's in the 7S, right? So you're going to have to end this thing with 4F, 5D, 6P, 7S. Just keep going. Come on, Dory. Just keep swimming.
Then 3D, 4D, 5, 6, 7. I got you.
6, 7.
5D, 6D.
Does that add up to 88? We've got a winner. Let me look real quick. I think I'm going to wait to show you the shortcut tomorrow. Maybe for homework I'll assign like
No.
an octave. I'm not going to. Good. I want you to do it wrong today. Sorry? Better end on 7, dude.
I got 7, but I still have 8 left.
What is 4F? Right here.
It's the one called 1.97, so you just have
14 is the bottom one.
14. It was not 14.